In 1891, a small town in Ohio tried something unusual. Instead of covering one of its roads with dirt, gravel, or the material people were used to, a local inventor named George decided to build it with concrete. At the time, cars are still a novelty. Nobody knew what modern highways would eventually look like. But that experiment turned something remarkable. More than a century later, part of that original concrete pavement still survives. And that leaves us with a strange question. If asphalt is cheaper, easier to repair, and often feels smoother under your tires, why would anyone build a road out of something as rigid as concrete? The answer isn't simply that concrete is stronger. A road is constantly being pushed, bent, heated, cooled, and loaded by thousands of vehicles. And sometimes even the cracks you see in the pavement are there because engineers wanted them to be. So why are some roads made concrete when asphalt seems like an easier choice? The answer begins with what happens every time a tire touches the road. Let's go get into right here on small things. A road is being bent every time you drive on it. A road may look solid and motionless, but traffic is constantly testing it. Every tire presses downward. A passenger car applies a load for a moment, then moves on. A heavy truck does the same with far more force, and on a busy road, that loading can return thousands of times every single day. Asphalt and concrete respond differently. Asphalt is known as flexible pavement. Stone, stone aggregate is held together by bitumen, a petroleum-based binder. The pavement is certainly not soft, but its structure can flex slightly as load move across it. Concrete is rigid pavement. Cement builds the aggregate into a much stiffer slab. Imagine placing a heavy box on a thick rubber mat, then placing the same box on a rigid wooden board. Both may support it, but the force reaches the surface underneath in different ways. The mat follows the pressure more closely. The board spreads more of that load outward. Concrete pavement uses that same basic advantage. The stiffness of the slab helps distribute the wheel's loads across a wide area beneath the road. For ordinary traffic, that distinction may seem unimportant. Add enough weight, repeat it often enough, and it becomes one of the main reasons concrete resists on roads at all. Where rapid loads change their equation. Picture the right lane on a highway packed with trucks, or a busy interaction with where loaded vehicles brake, stop, and pull away from nearly the same spot all day. The pattern repeats in freight yards, industrial sites, and airport pavement. Heavy loads keeps returning to the same sections of pavement. Asphalt can handle trucks. Well-designed asphalt roads do it every day. The problem is not a single heavy vehicle, it is what repeated loading can do over time. Depending on temperature, pavement design, traffic, and the structure underneath, a flexible surface can slowly change shapes. Where where paths may settle into shallow ruts. Depressions can form where loads repeatedly concentrate. This is where concrete earns its place. Its rigidity becomes valuable when resisting permanent deformation, matters more than allowing a pavement to flex. That makes concrete attractive for certain truck routes, busy intersections, industrial areas, and airport surfaces. Properly designed and maintained, it can keep much of its shape while enduring demanding traffic for a long time. But, stiffness solves one problem by creating another. A concrete road does not need a truck sitting on it to experience stress. Leave the road completely empty and another force is already at work. The weather. The road moves even when no cars are on it. Concrete looks like stone, but it never becomes completely moveless. Warm it up and it expands, cool it down and it contrasts. The movement is tiny across a short distance across the pavement slab. Those tiny changes matter. Imagine pouring one enormous stripe of concrete and preventing it from moving at all. As temperatures rise and fall, stress would build inside it. Eventually, the material would find its own way to release that stress, potentially by cracking somewhere engineers did not expect. That brings us back to those lines you can see and hear while driving. Many are joints created deliberately. Instead of treating the entire road as one continuous slab, engineers divided into manageable sections. The joints give it a pavement control places to accommodate movement and relieve stress. These are an important distinctions here. A joint is not simply a crack, but every crack in a concrete road is intentional. Engineers can, however, create weakened planes so that shrinkage cracking is more likely to occur along uh, pre- predetermined, predetermined lines rather than wandering unpredictably through the slab. Some pavement designs also use steel reinforcement to help neighboring sections remain aligned and work together. So those gaps are not evidence that evidence failed to make the road continuous. They deliberately chose not to. What looks like a weakness in the pavement may actually be one of the things protecting it, which creates an obvious question. If engineers can control concrete this carefully, why is asphalt as it's still everywhere? So why isn't every road concrete? Because the road has to do more than survive traffic. It has to be built, repaired, reopened, and paid for. That is where asphalt has advantage concrete cannot simply erase. Asphalt can often be placed quickly, com- compacted, compacted, and returned to traffic relatively soon. Concrete construction usually requires more preparation, careful placement, and enough time for the material to gain strength before carrying normal traffic. Then comes maintenance. When an asphalt surface where crews have several options. They may patch a damaged area, remove the worn upper layer, or place a new surface over the existing pavement. Those repairs can still disrupt traffic, but the process is often relatively flexible. A seriously damaged concrete slab can require a different kind of intervention. The affected section may need to be cut off, removed, replaced, and allowed to gain strength before the lane fully returns to service. Asphalt also tolerates certain small movement beneath the pavement more readily. The contrast is simple. Concrete is designed to resist particular kinds of deformation, while asphalt is more willing to move with the structure beneath it. Neither approach answers every road has problem. So the engineers are not really deciding which material is better. They are deciding which disadvantages they are willing to live with. The real choice is trade-off. Road designers have far more to consider than strengths. How much traffic will use the road? How many vehicles will be heavy trucks? How hot and cool will be the pavement become? What kind of ground lies underneath it? How much how much can construction cost? And if repairs are needed a yearly later, how difficult it would be to close the road. Then comes the long-term question: how often will major work need to happen? A pavement that costs more on opening day may still make sense if it performs for many years with fewer major interventions. But a surface that needs renewal sooner can still be a smart choice if network is quick, affordable, and causes less disruption. This is the basic idea behind life cycle thinking. The cheapest pavement to build is not automatically the cheapest one to own the own for decades, and the pavement capable of lasting the longest is not automatically the right answer if keeping it working requires expensive and disruptive repairs. Road design is not about building the longest lasting surface. It's about choosing the kind of lifespan that makes sense for that road. That is why gray concrete and black asphalt continue to exist side by side. Their coexistence is not evidence that engineers have failed to choose a winner. It is evidence that a problem has more than one useful answer. Concrete roads are older than they look. Concrete pavement may feel like a product of an product of modern highways, but engineers were experimenting with the idea a long time before today's road networks existed. An early Portland cement concrete pavement was built in Scotland in 1865. In the United States, George created an experimental concrete pavement in Ohio in 1891. 2 years later, a larger section followed, and part of that historic pavement survived. The vehicles of that era looks nothing but looked nothing like today's trucks, buses, and airliners. Yet the basic engineering problem was already recognizable. How do you build a hard surface that can carry repeated traffic without quickly losing its form? More than a century later, engineers are still balancing different answers to that same question. And drivers can sometimes identify which answer they are riding on without seeing the road at all. They only have to listen. The sound under your tires is part of the design. Sometimes the pavement announces itself before you notice its color. On a concrete highway, your tire may settle into a faint rhythm as they cross the transverse joints. Asphalt often feels more continuous, although road noise also depends on surface texture, age, wear, and condition. That repeated sound from concrete is more important is more than an anonymous or a creak of the road. You are hearing part of the road structure pass beneath you. Each beat marks another boundary in pavement deliberately divided into sections. What looks from above like a simple gray surface is actually a system designed around movement, stress, and control. That is one of the strange things about the roads. Much of the engineering is hidden precisely because it is walking. You notice the black asphalt, you notice the pale concrete. Maybe you notice the sound, but believe that those ordinary details are two different answers to the same question. How should a road survive everything that will happen to it? So why are some roads made of concrete when asphalt seems smoother and easier to repair? Because concrete offers something valuable in the right conditions. A stiff pavement capable of spreading heavy loads and resisting certain kinds of deformation over a long period. Asphalt offers a different set of advantages, especially when construction speed, flexibility, and easier resurfacing matter more. The choice depends on what that particular road is expected to endure, and that brings us back to the detail that started the whole question. The most visible flaws is in a concrete road. The gaps running across it maybe exist exactly what allow the rest of the pavement to survive. Those lines are not merely interruptions an in an otherwise perfect road. They are reminders that engineering does not always mean preventing movement or avoiding every crack. Sometimes it means deciding where change is allowed to happen before nature makes that decision for you.